Welcome back to the Deep Dive, where we dig into the latest technical sources, the case studies, all the operational guides, and really just distill them down into what you actually need to know. Today, our mission starts right where most guides stop. So you've done it. You've spent weeks, maybe months, getting your large language model perfectly tuned. The evils look amazing. You've got the perfect recipe. But as anyone who's ever tried to run a real service knows, the model is done is a totally different thing from users are hitting a stable endpoint that isn't on fire.
It is. And we're going to lean on this really fantastic analogy from the source material to guide us through this. The leap from development to deployment. It's exactly like opening a restaurant.
Okay, a restaurant. I like that.
Yeah. So our mission today is to unpack those necessary kitchen protocols. We are shifting the focus entirely. We're moving from the elegance of cooking, say, one perfect dish in isolation, to the gritty survival of a chaotic dinner rush.
Simultaneous orders, running low on inventory, equipment failing.
Exactly. And the core insight we want you to walk away with is this. The weights, your recipes, they might not change, but the robust system around them is what determines whether they survive service.
Ah,
Okay, so let's unpack the difference in operational responsibility first. Because this is where a lot of teams, especially when they're transitioning from experimentation to deploying it, just get completely caught out. If you're used to leveraging a managed API, like OpenAI or Gemini, you're basically ordering takeout.
mm-hmm.
You pay your fee, and you don't give a second thought to their infrastructure. If the provider's oven breaks down, that is entirely their problem.
Precisely. Managed providers abstract away all that critical heavy lifting. They handle sophisticated techniques like batching.
Which is just grouping multiple user requests together to be more efficient.
Right. To squeeze the maximum amount of work out of an expensive GPU, they ensure memory safety.
Preventing the dreaded OM crash.
The out-of-memory crash, yeah. It happens when a huge flood of orders arrives at the same time. And what's vital for user experience, they manage cold starts. Ensuring the system is always warm so the first user request isn't sitting there waiting for 60 seconds for the model to load.
But when you choose to self-deploy that specialized, fine-tuned model, you've basically decided to run the entire restaurant, from the front of house all the way to the garbage disposal. All that responsibility just lands squarely on your team.
And the problem isn't just the sheer amount of work. It's that your specialized model introduces new fragility. You spent time and money narrowing the model's focus to improve quality on a specific task, say, summarizing legal contracts. That specialization makes it inherently more brittle than a generalist model trained on, like, the whole internet.
Okay.
The sources highlight two major issues here. First, what they call outsized effects. Small changes in how you format the input, the preparation, can cause massive sudden drops in quality.
So if I train my model only on prompts that began with instruction, and I deploy it, and then some client sends a request that just starts with, please do this, that tiny tweak could send the quality into a tailspin.
It absolutely could, and we need to ask why. It's often because of the limited scope of the fine-tuning dataset. You've traded generalization skills for peak performance on a really narrow task, so that model learned to perfectly mirror the format of its training data, and any deviation becomes a major disruption.
That makes sense. It's like a specialized chef who only knows how to perfectly execute 6 dishes. They'll panic if you ask them for a 7th.
Exactly. The second issue is distribution shift. This is when unexpected inputs arrive, ingredients that don't match the training data. If your model, which is optimized for contracts, suddenly gets a dense geopolitical policy report, it can suffer a catastrophic performance failure. A generalist model, which has seen pretty much everything, would handle that with, relative grace. You have to anticipate that input drift in production.
So this brings us to the core philosophical difference, the production mindset. If training is all about optimizing the waves, getting that recipe perfect, then production has to be about optimizing behavior under constraints. What specific constraints define this new environment?
Well, we're moving beyond just accuracy. Now we care about things like latency budgets. Users will not wait forever. We care about memory limits, the number of concurrent orders the GPU can handle, and fundamentally the cost constraints. A model that scores 98% on your evils can still be a production failure if it collapses under a load of 50 simultaneous user requests because it just can't manage the memory.
And that leads naturally into right-sizing your deployment. You wouldn't invest in a massive industrial kitchen to run a weekend food truck, right?
Yeah.
The infrastructure has to match the scale and the criticality of the service.
That's vital. If your model is simple, only used internally, low traffic, non-critical. Manual deployment scripts and ad hoc rollbacks, like a controlled test dinner, that might be fine. But if external users are involved, if revenue depends on the outputs, or if your prompts are changing all the time, you need robust, automated systems.
Okay, so moving from technical fragility, let's look at the financial tightrope. This is the economic difference, the cost trap.
Yeah.
Managed APIs are beautifully simple. They are a la carte, pay per token, send 0 requests, you pay $0.
Self-hosting flips that model entirely because you are paying rent on the hardware itself. The sources note that a high-end GPU, something like an A100, can cost upwards of $5 an hour, whether it serves 10,000 requests or just sits there idle. This dramatically changes the economics for any application that isn't running at peak capacity 24/7.
Can you give us a concrete example of that cost trap?
Sure, imagine you rent that A100 for, say, $3 an hour, but your traffic is sporadic. Over an 8-hour day, you only process 80 total requests. You still paid $24 for the hardware. That means you paid $0.30 per request just for the GPU rent.
Well, compare that to a managed API, which might charge, what, 0.0005s per request? If your traffic isn't high and steady, your operational costs can just far exceed the API costs, making self-hosting a financial disaster.
That's the key takeaway right there. You're paying rent on an empty kitchen, and suddenly the cost per dish is just astronomical. The solution then, for teams with unpredictable or bursty traffic, is to avoid that 247 rental model entirely.
Yes. For teams still scaling, or those who see heavy peak usage followed by long periods of inactivity, the sources suggest utilizing serverless GPU options like Modal or RunPod. These let you pay for active processing seconds instead of paying that constant hourly rental rate. It's like turning the kitchen lights off when there are no orders.
Okay, let's make this actionable. We're going to use a single node deployment running VLLM as our concrete reference point since it's a widely adopted standard. But before we dive into the essentials, let's just quickly acknowledge why we even need frameworks like VLLM or TGI or TensorRT LLM. That's a great framing point. You can't just run a simple Python script in production. You need these complex mechanisms to manage the shared, expensive GPU resource. These frameworks, particularly VLLM with its page detention architecture, exist specifically to handle efficient batching and predictable memory management. They make sure the system doesn't crash from an OMR when your concurrency spikes.
So these frameworks are the necessary kitchen management system that lets us handle multiple orders without dropping plates. We've synthesized the sources into 8 essentials that turn a robust script into a resilient production-grade service. We'll start with consistency.
If we've established the right weights and parameters, the next logical step is making sure the inference engine itself doesn't shift under us. That brings us to Essential 1, stack determinism.
Pin your stack, don't rely on latest.
Exactly. You must lock to exact specific versions. VLM x.xx, Torch x.xx, specific CUDA, and driver versions. Why? Because subtle changes in the underlying inference engine or the drivers can alter the model's behavior even if the model weights are identical. And that lack of deterministic output is just a nightmare to debug.
Okay, next. Essential 2. Behavioral consistency. This is about locking the generation parameters. Don't let your clients mess with the recipe after you've already perfected it.
Right. Exploration is for dev and evil. Production requires predictability. You have to lock in defaults like temperature 0.7, max tokens 512, and the stop sequences you need. If every client is allowed to send different parameters, your model's outputs will drift and become completely inconsistent over time. It makes quality monitoring impossible.
Moving on to Essential 3. Artifact separation. Immutable files. This is the core of our restaurant analogy.
Yeah.
You never store the massive version recipes with the constantly changing daily orders.
You need independent versioning. Model weights are huge, 50, maybe 70 gigabytes, and they might change monthly. Prompts and config files are tiny kilobytes, and they might change daily. If you lump them together, I can just hear the deployment engineers screaming when they realize they have to reload 50 gigabytes just to fix a single misplaced comma in a system prompt.
So the crucial structure here is separate, immutable model weights in a models folder, version prompt templates in prompts, and explicit runtime configs in config. And there's a cardinal rule about that models folder. It must contain everything local.
Absolutely non-negotiable. No runtime downloads from Hugging Face or any external network on startup. If your code tries to pull weights and the network blips for even a second, your entire service fails to start. Resilience is built on local, immutable files.
Okay, so before the request even hits that expensive GPU, we need a bouncer at the door. This leads us to Essential 4. Input and output safety, the request boundary.
This is your first line of defense for controlling cost and latency. You need to validate and reject expensive requests before they consume precious GPU time. This means checks on max input characters, Rough token estimates like rejecting inputs estimated over 6,000 tokens, and enforcing a maximum output length. Crucial portion control.
So we're stopping a bad request from crashing the system. But here's a critical decision. When we hit that capacity limit, do we queue the traffic and make users wait, or do we reject it?
That's a key moment. And while it sounds customer-friendly, the sources are clear. Early in deployment, it is far safer to reject requests rather than queue them.
Why is that?
Queuing hides overload. Latency just creeps up slowly, and by the time you notice, the entire system is paralyzed and everything fails at once. Failing fast and returning a clear 429 status code, too many requests, it keeps the overall system responsive. You give the customer a clear signal instead of just leaving them hanging indefinitely.
That makes a lot of sense. Better affirm, no, try again in 30 seconds, than a 5-minute silence followed by a crash. Okay, now we transition from what goes into the system to how we watch the kitchen during the dinner rush. Essential 5, observability. This is the difference between hoping nothing goes wrong and knowing exactly why it did.
We need tight visibility because, as we said, fine-tuned models are incredibly sensitive. We need to track what the sources call the kitchen fire manifest. Most crucial is time to first token, or TTFT.
Right, TTFE.
This is the key measure of perceived speed, the time from when the user hits send to when the very first token appears on their screen. If that spikes, users feel the slowdown instantly.
We also need to track P95 latency, so the experience for the slowest 5% of users and things like error rates and GPU memory usage.
Yes, and you must monitor tokens per request. As the average complexity of what users are asking slowly creeps up, your total capacity drops and costs explode. Regarding logging, strategy matters. Early on, log nearly 100% of requests to get your baseline. But at scale, you can sample successful requests, maybe 1% to 10%, but always log 100% of errors and 100% of latency outliers, like any request taking longer than 5 seconds.
Let's talk about managing the actual physical resources. Essential 6, resource management and capacity. This speaks directly to the defaults trap we mentioned earlier.
Defaults are treacherous. They assume a general use case. You have to tune your inference engine explicitly. 2 flags are critical. First, max model in 8192. This is a hard cap on the context window. Requests that exceed it must be rejected outright, not silently truncated, because truncation often gives you useless results anyway.
And the second flag is directly tied to preventing that capacity dilution.
Right. GPU memory utilization 0.90. This reserves memory upfront. The sources recommend starting conservatively, maybe at 0.85, because running out of VRAM isn't a performance snag. It's an uptime disaster that requires a full system restart. You have to treat GPU memory differently than standard RAM.
And how do we find our true, reliable capacity?
You measure it. You push concurrent requests until your TTFT or error rates spike unacceptably, that number, that's your real capacity. And until you've measured that limit, you default to rejection over queuing to ensure stability.
Okay, moving to Essential 7, deployment strategy, the rollout. Our goal is to limit the blast radius when we introduce a new recipe or ingredient.
The phased approach is non-negotiable. Phase 1, shadow traffic. You send production requests to both the old model and the new one. The new model processes the request silently, you log the performance, you log the quality, but you never show the result to the user. This is just passive testing.
And once that looks stable,
you move to phase 2, canary. You route a very small portion, say 1% to 5% of users, to the new model and let them see the results. And you watch immediately for customer complaints, quality regressions, latency spikes. Only after all that looks good do you cut over to 100%.
Finally, Essential 8, operational resilience. When things break, and they will, how does the system recover gracefully? This is where liveness and readiness checks become the bedrock of uptime.
And you cannot confuse them. Liveness is the basic "are you there?" ping. If that fails, the system is dead and it must restart. Readiness is the "can you cook?" check. It actually attempts a tiny token generation. If that fails, the system stops sending user traffic but keeps the model running, giving it time to load or recover internally.
That readiness probe is the shield against the reality that large LLMs take time to load.
Precisely. They can take 30 to 60 seconds to load into GPU memory after a restart. The readiness probe prevents the first 50 users from hitting the server during that critical loading window and just seeing a stream of 500 errors. You also need graceful shutdowns. When you deploy a new version, the old server has to stop accepting new requests but stay alive for 30 to 60 seconds to finish the current generations. This prevents those mid-sentence cutoffs for users already in a conversation.
And defining failure paths is the final act of resilience. Whether it's rejecting requests with a 429 when capacity is hit, or implementing circuit breakers.
Right, like stopping new orders if 5 consecutive requests fail to give the server time to stabilize. You must make an explicit decision on how the system fails. It's better to tell a customer we're at capacity than to just leave them hanging indefinitely.
Okay, we've covered the 8 steps. Let's quickly summarize the common pitfalls that usually cause production disasters, linking them back to what we just discussed. First, the defaults trap.
Ignoring Essential 6, resource management. You trust the defaults, the context window grows unchecked, memory gets overcommitted, and the server inevitably falls over. The second is phantom changes, ignoring Essential 3. Prompts get tweaked outside of version control, quality instantly regresses, and nobody can figure out what changed because the engineer didn't touch the model weights.
The third is the capacity delusion, ignoring input safety and resource management, treating VRAM like it's standard RAM. Running out of VRAM isn't a slowdown, it's a crash that requires a lengthy reload.
And finally, testing only the happy path, ignoring Essential 8, failure logic. You only test short, clean prompts, but real users send malformed JSON strange characters requests that are too long. If your failure logic isn't tested, that first edge case takes down the entire service. The core message is that good deployment practices don't eliminate problems. They make them solvable and visible.
That is the ultimate goal. Fine-tuning provides the recipe, but deployment discipline lets you serve it reliably for the long term. You're done when you stop guessing about capacity, and your system automatically tells you, via those observability metrics, when you're reaching your limit or when quality regresses.
The sources raise a really important question that follows opening night. Once you're live, user input data will invariably drift. The average complexity of those inputs, the complexity of the ingredients your kitchen receives, it will probably creep up over months. So if your system is designed around specific latency and cost boundaries today, what mechanisms beyond just logging do you need to build in to automatically alert or adjust when that slow, invisible shift fundamentally changes your GPU capacity profile? That is the invisible maintenance challenge for tomorrow.
A profound challenge to consider as you build out your architecture. Thank you for joining us on the Deep Dive. We hope this roadmap to production LLM infrastructure helps you open your restaurant successfully and keep it running for the long term. Keep learning, and we'll see you next time.